Alright, so now I'm going to do some cleanup. There's this one gap that we left in our proof of the special case of the inverse function theorem, proving that the inversion function from invertible linear maps to invertible linear maps is a continuous function. So fix a natural number greater than or equal to 1, and let's use omega to denote the set of invertible linear maps from Rn to Rn. And I'm gonna use the word inv to refer to the mapping A to A inverse. Okay, and my claim is inv is a continuous function. Okay, so continuous means continuous on its entire domain. So let's fix a point in the domain and show it's continuous at that point. Unless I'm trying to show it's uniformly continuous, but I don't think it is, at least. I'm not sure, but I don't think it's uniformly continuous. Anyway, we're just showing it's continuous. So let's fix A in there. So that means A is an invertible linear map. Now let epsilon be greater than 0. And then we need to choose a delta that works for proving that inv is continuous at A. So let delta equal, and sometimes I say let me figure it out later, but I'm just going to tell you what it is. And I'll explain as we go along how I came up with it. So I've got some notes here, and I'm just looking and copying down what delta is. So it's the minimum of these two numbers. One of them is going to be 1/2 1 over the norm of this linear map A inverse. A is definitely invertible. It's in this set of invertible linear maps, and I'm not dividing by 0. The norm of a linear map can only be 0 if the linear map itself is 0. And the second number I've got here is epsilon over 2 norm A inverse squared. Okay, so just accept that, and as we go along, you'll see where they came from. Okay, now let B be an omega such that the distance between B and A is less than delta. Or if you prefer, B is in the delta ball centered at A. And now we need to prove that B inverse, the inv function applied to B, minus A inverse norm is less than epsilon. So that is our goal. And what I'm supposed to convince you is that this choice of delta ensures that. So the reason I'm saying let B be in omega rather than saying let B be an arbitrary linear map is that when you're proving a function is continuous when you're proving a function is continuous, you only pay attention to points in its domain, right? So this should not surprise you that I'm saying that, but one thing that we don't need to prove, but that is nice to know, is that omega is actually an open set. And so I'm not proving that just because we don't necessarily need it. But it's nice to know. Omega is an open set. So that means if I chose delta small enough, maybe the minimum of 3 numbers, maybe if I included a third number here, then I could guarantee that this automatically, just by virtue of B being close, delta close to A, which is invertible. So when I say omega is an open set, what you should imagine is if a linear map is close to an invertible linear map, close enough, then it must itself also be invertible. So that's just nice to know, but we don't need it. All right, so let's just start working with B inverse minus A inverse and see if we can make B minus A come out. So the first thing that comes to mind is that we can pull out an A, or rather pull out an A inverse, like this. So if I pull out an A inverse, then this is identity map, or I think I've been using this notation, identity map on Rn. And this is A composed with B inverse. So that's pulling out an A inverse on the right. Then I can pull out a B inverse. Sorry, that was pulling out an A inverse on the left. Now I can pull out a B inverse on the right. So pull out a B inverse on the right, just like that. Then this becomes just A, and then this one becomes B. And look, I've got A minus B here. So then the norm of this is the norm of this is the norm of this is less than or equal to this product of norms. So I'm using this property of the norm on the vector space of linear maps, having to do with what happens when you compose linear maps. You get this inequality. So let me show you exactly what I'm using. Here in Rudin, I'm using this portion of Theorem 9.7. So this is one of the properties of this norm with respect to composition. Okay, so that's pretty good, because now I'm trying to get this to be less than epsilon, and what I control is this, and look, I made it pop out. So this looks pretty good, and it might now be tempting to say, oh, we're basically done. Now just, why did I choose this crazy, weird-looking delta? Why not just say, how small do you want to make this? Just make it this small. How about that? Why don't we just do that? If I did that, then here I would say, oh, less than or equal to epsilon. Less than epsilon. Right? So why don't I do that? So you've probably seen this situation many times before in analysis. This does not make any sense, right? Where do I choose delta? Up here. Before I fix B. B needs to be fixed in a way that depends on delta. So it does not make sense to make delta depend on B and then go and make B depend on delta. So this would just not be logical. This is like one of the lessons you learn very early on in analysis. All right, so what do we do then? By making this small, we can make the whole thing small, except as B varies, this portion varies. So we need to get this portion under control. And this step kind of reminds me a lot of something we saw in 118A. So here is our 118A textbook, Abbott, and this is the algebraic limit theorem. It reminds me of this step where we were working on the limit of a quotient of two sequences where the limits of the individual sequences exist. And here was the proof of this portion of the algebraic limit theorem. And the problem was, when you look at this, the distance between 1 over bn and 1 over b, you get this thing that you control, b minus bn, but you also have this bn in the denominator. And, the problem is, yeah, you can make this small, but how do you know bn isn't also getting small along with it? And if bn is also getting small, then maybe it'll not allow you to control the size of this thing. So to get this situation under control, you need to make sure that bn cannot be too small. This is a really similar situation that we're in now, where in our situation we have this, and we're worried that it might get too big. Now, one thing we cannot do here, it's tempting to say, oh, this is basically the same setup because you can rewrite this as this. That's quite tempting to do when you're used to, you know, the absolute value symbol from doing one-dimensional real analysis. But this is super extremely wrong. We don't necessarily have this. So the situation is a little different, but it just reminds me of that one. All right, so now you know why delta is the smaller of two things. One of the things, it'll turn out this one, is to control this overall expression here, and the other one, it'll turn out this one, is to ensure that the norm of B inverse isn't too big. It's reasonable to think that you could maybe control the norm of B inverse. By choosing delta, you make B be close to A, right? You make B be close to A. It should be that if B is close to A, then B inverse can only be so big, can only be so far away from 0. So it at least feels right, I think. Okay, so let's see if we can get this norm B inverse under control. So let's think about applying B inverse to a vector. So for x in Rn, let's say with norm x less than or equal to 1. Remember, the norm of B inverse is the maximum value of the norm of B inverse applied to x for all x's like this. We have B inverse x norm, and this is going to be kind of tricky. So this took me a little while to fiddle around with and figure out how to get this to work. So I'm going to apply A inverse and then A. So that's definitely right. Then think about it like this. I've got A inverse getting applied to this vector. So that's going to be less than or equal to the norm of A inverse times the norm of this vector. Now on this portion, I'm going to use the triangle inequality. Remember, the thing that I think is going to control the size of this is the fact that B is close to A. So I'm trying to get norm A minus B to come out somewhere here. So what I'm doing here is an effort to make the norm of B minus A come out. So here I'm going to apply the triangle inequality, hence the less than or equal to here. So A B inverse x minus x plus x. So I subtracted and added x, and then I used the triangle inequality. Like that. And this is being multiplied by something non-negative, so the inequality stays like that. So another way to look at what's happening here, well, actually I want to get a minus b into the picture. So let me rewrite it like this. So this is A applied to B inverse x minus B applied to B inverse x. Like that. And so that's A minus B applied to B inverse x. plus the norm of x. Okay, and this is bounded above, so linear map applied to vector. I think the norm bars disappeared, sorry about that. The norm of linear map applied to vector is less than or equal to the norm of the linear map times the norm of the vector. So using that feature of the norm of linear maps, the norm of B inverse x. Okay, so I did successfully make the norm of A minus B appear, and also I've got B inverse x sort of showing up on both sides. So let me look at the overall inequality and combine the B inverse norm of B inverse x terms. So let's see. Maybe I'll divide both sides by 1 over norm A inverse. So 1 over norm A inverse, norm B inverse x is less than or equal to, so that's the left side divided by norm A inverse, is less than or equal to this. So now I'm going to combine these two terms. So I'm going to subtract this from both sides. And I have 1 over norm A inverse minus A minus B norm, all times B inverse x norm is less than or equal to the norm of x. Okay, so this is starting to look pretty good for managing the norm of B inverse x. And you know, I set things up here so that the norm of x is less than or equal to 1, right? So this is less than or equal to 1. And whatever upper bound I get for the norm of B inverse x, that's going to be an upper bound for the norm of B inverse. So that's by the definition of the norm of a linear map. Okay, so let me divide both sides by this, and there's my upper bound for the norm of B inverse x. So 1 divided by this. Okay, but can I divide by this? Maybe it's 0. Well, remember, I get to control this. I get to make this less than delta, and I get to choose delta. So let's make it small enough that that I'm not dividing by 0. In fact, let's just choose a standard of smallness for how small we want to make this. So look over here. Now you see why I made this choice. 1/2 1 over norm A inverse. So this here is less than 1/2 1 over norm A inverse. So we have, you know, whatever I write here should come before I potentially divide by 0, right? So let me bring this up here. We have this is, okay, so the norm of A minus B is less than delta, so this, you know, this minus the norm of A minus B is greater than, well, it's strictly greater than that minus delta. And delta is the minimum of two things, one of which is 1/2 1 over the norm of A inverse. And so I've got something minus half of itself. Great. So the denominator here is not 0, so I can do this division. And also, I have an inequality. So the denominator is greater than this, so that means the fraction here is less than is less than 1 over this. And look at that. I have an upper bound for B inverse x when x is a vector of norm at most 1. So that is a nice upper bound for the norm of B inverse. So the norm of B inverse is less than or equal to 2 the norm of A inverse. So this is not a general fact, but it's guaranteed by our choice of delta, this portion of our choice of delta. Okay, great. So let's go back to where we needed to control the norm of B inverse. That was here, right? So now let's look at the distance between B inverse and A inverse and continue from over here. So let me just copy this actually. I'll be right back after I figure out how to move this nicely. All right, there we go. So, I think this proof is really lacking some words. Then, there we go. Now it's a sentence. So then, this we're trying to get this to be less than epsilon, remember? So this is less than or equal to this. So that's less than or equal to, I think this was a less, well, I don't know. Whatever. This is less than or equal to this times, well, let me just fill in delta for this. And then for this, I'll put 2 times that. So that's 2 this squared times delta. Okay, and now you can see where my other choice of delta came from. If you go way back to where delta was chosen, epsilon over 2 norm A inverse squared. Delta is less than or equal to that. So this is less than or equal to this thing, which is epsilon. All right, so we have proven that inverting a linear map is a continuous operation.